Hi everyone. So in this video, I'm going to talk about the liver disease classification data set. And the goal of this task is to predict whether a patient has a severe cirrhosis defined as a stage 4 and using clinical and laboratory measurements. So this is a supervised binary classification problem, and I will walk through the key pre-processing steps and the models used and the validation methods and the insights from results. So basically, the data sets comes from a Mayo Clinic study with a total of 418 patients, and the data sets includes numerical variables such as age, bilirubin, and also includes categorical variables like sex, um, and drug types. So the data sets uh, each row represents one patient. So after loading the data, we can see that many columns contain missing values, especially uh, cholesterol and copper. So we first um, drop ID column because it has no predict value. So next, um, we handle missing values. We handle the missing values. Numerical features were filled with zeros, and missing categorical values were filled with a placeholder category. So this allowed us to keep as many observations as possible instead of just dropping rows. So originally disease stage has values from 1 to 4 but to simplify the problem, so we converted into a binary target. Stage 4 was encoded as 1 and representing severe cirrhosis, and all other stages were encoded as 0. So some numerical variables such as um, bilirubin and cholesterol were highly skewed. So we applied a log transformation to reduce skewiness, and outliers were adjusted using Windsor ration, which limits extreme values without removing observations. So categorical variables were converted into dummy variables using one-hot encoding. And finally, a subset of key numerical predictors were selected, including NDAs, prothrombin, bilirubin age, and so on. So after pre-processing, we checked class balance. About 34% of patients um, are in stage 4, which indicates moderate class imbalance. And a correlation heat map showed that allabin and NDAs were negatively correlated with cereal disease, which while bilirubin and prothrombin were positively correlated with stage 4. These relationships are clinically reasonable. So for modeling, we use the 80-20 chain test split, which is a holdout validation method. Before training, numerical features were standardized using a standard scalar, and smooth was applied only to the training data to adjust class imbalance and avoid data leakage. So the first model was a decision tree. Decision trees are easy to interpret and can capture nonlinear relationships, but they tend to have high variance and can overfit the training data. And the decision tree is about achieved about 60% accuracy on test set based on the confusion um, matrix. So in terms of bias variance trade-off, logistical regression usually has higher bias, but um, lower variance and offers strong interpretability. A decision tree has have a lower bias but higher variance, which explains their tendency to overfit. To reduce variance, we used H2O and AutoML, which trains multiple models and evaluates them using cross validation. So uh, ML automatically train multiple models, including tree-based combos, and uses fivefold cross validation with class balancing enabled. This helps reduce variance and usually leads to more stable performance. So results show that laboratory measures such as um, uh, al albumin, bilirubin, and are strong indicators of advanced liver disease. And in real-world applications, this type of model could be used as a clinical decision support tool to identify high-risk patients earlier. And in summary, this project demonstrates a complete machine learning workflow, including processing, validation, bias variance consideration, and model comprehension. It also highlights the trade-off between interpretability and predicted performance in healthcare application. And thank you for your listening.看多久？